Okay, so I think we can start. So thanks everyone for coming. We have the pleasure today to have Nils, which is a second-year PhD student at Copenhagen University and the German Research Center for AI in Berlin. His research interests are self-supervised representation, low-resource language, low-resource learning, interpretation, generalization, continual transfer learning, and medical AI. So Nils will start in a moment. If you have any question, please feel free to raise your hand during the talk, and we'll refer you to direct Nils. Or at the end, we'll collect a question through Dory, and also just raise your hand, and hopefully we can have a nice conversation. And that's it. And Nils, you can start.
Yes, for the introduction. I would like to into it. So I want to talk to you about today evaluating and explaining. Okay. Transferable text representations from small data. And this is work done in part with my supervisor, Isabel Augenstein, and also with my colleague, Vagish Saxena. I want to start off with the XAI part. And first of all, I want to kind of define what I think explain and interpret means, and I lean that interpretation heavily on this work that I link here. So they have this very interesting view. The first thing that they mention is decision understanding, and for me that mostly maps to explainability, where you kind of see the model as a black box. And by this kind of explainability, I mean that you explain your input to output task relevance, which means this basically what we know as this heat mapping, that you say, okay, how important are these features for that label, as you can see here on the right. Of course, this needs supervision labels, but you can also get away with incidental labels or self-supervised labels. And also this often explains a single instance. So you have to look for your entire corpus over a lot of instances to really understand what's happening. On the other side, they also have this notion of model understanding, which I mostly see as interpretability or gray box methods. And here, one way of doing this is to interpret neuron activity over an entire corpus, irrelevant of your outputs. It's not entirely irrelevant of your output, but because there's a lot of reweighting happening in upper layers, you don't really get this direct correlation to your labels that you have, if you have any. So you can kind of see this as a self or unsupervised method of interpreting networks. It also allows you to prune unused neurons or to find redundant neurons. And I will talk about this in a bit later in the talk. The first paper I want to talk about is paper about transfer XAI and measuring transfer using XAI. And our motivation for this was that supervised probes limit really what you can understand about your network, because they're first of all limited to supervision, so they can only probe what you expect the network to have learned, and you cannot really discover anything unforeseen within your network. And then there's also this problem if your probe is from a different domain. Let's say your pre-training text is from one domain, your probe text is from a very different domain. It might not be that meaningful what your probe does. So actually what we want to ask here is, we want to see if we can somehow get closer to model transfer understanding at the individual neuron level. And for this, we'll go through 3 research questions. The first one is, how does self-supervision build knowledge abstractions? Then when we zero-shot apply these learned abstractions to a new corpus, can we show transfer? And how can we measure it and visualize it? And then also, of course, if we do fine-tuning, what happens to our representations? And the way we do this, like the technique we use this is a self-supervised interpretability method that by now is quite old. It's from 2009 and it's called activation maximization. It's still heavily used in vision. And what it does, it visualizes what input features each neuron prefers, i.e. maximally activates on. So let me explain this a bit in detail. There's two methods here in vision. You can ask for each neuron, you generate the input that maximally activates that neuron, and then you know kind of what pattern that neuron prefers in a sense. However, in both vision but also NLP, you can simply record for each input feature that you get which neuron it maximally activates. So let's say here on the lower right, we have the sentence, I like cake better than cookies, and we feed that into some text encoder. We could say that the first neuron maximally activates for the feature cake and cookies. So each feature that you have in the input in each instance only is mapped to one specific neuron because of this maximum activation notion. Then you might also have another neuron here that only likes I and then. And this basically gives you then, you have one neuron that prefers sweets and another one that prefers stop words. Of course, in reality, things are a bit more messy. This leads us to the first question, because we often do this self-supervised pre-training. Here we pre-trained an LSTM encoder, single layer, very simple, because we wanted to look at how to analyze transfer, not at crazy architectures or things like that. And what this gives you is, here in the lower left, it gives you basically this token preference distribution for each neuron, so what each neuron prefers. And one thing that we wanted to see is, how does this learning actually work throughout training epochs? So here in gray, we see epoch 1. Then we train this for 50 epochs until convergence, and you also see epoch 49 and 48. So beginning and end of training, kind of. And what you can see here is we get activations for all these words, but we don't want to plot thousands of words on an x-axis, because that just becomes a huge plot that is unreadable. So we use part of speech text to kind of cluster these words, just to have a more compact plot in the end. And what you can see here in gray is, in the first epoch, you get this one part of speech tag, and you get this one word. And then red, you still get the same part of speech tag and the same word in later epochs, just it activates a bit more strongly. So overall, you can kind of say that this neuron was already initialized to the training process, but it's also kind of very specific, because the only word it really prefers is with. So it's kind of the with neuron, which is very over-specialized, at least the way I see it. Here's another neuron that, again, in gray, started out with one part of speech, and then we can see that we have 3 bars for 3 different part of speeches, and we can also see that the word in the first epoch was condition, and later on changed to leader, mothership, goals, and he. So it didn't move that much in the later epochs, but it completely moved from the first epoch. So this neuron was really trained and reconfigured in the process. And when I talk about transfer in this, even though in the pre-training setting, it's not quite that obvious yet, what I mean is, if you take this representation that you have and then change it to a new training objective or a new data set, and it doesn't change much, then you have high transfer of that neuron's representation, basically. If it changes a lot, then you have a reconfiguration, which means it didn't transfer that well. So let's have a look about...
So, Nils, I have
yes?
a question on that. So, like,
yeah.
how can you say something about how is this neuron transfer to other tasks if it's only the pre-training? So, like, why does it matter the neurons?
Here, good question. Not yet. I will talk about that in the second research question, zero shot and supervised. However, this was maybe a bit early on. I will come to that in like a minute. Okay. One thing I want to point out here is, if you look at these 2 specific neurons, and this is only like a post-hoc reasoning, this is not in the paper at all. To me, it seems a bit like the self-supervision as next word prediction. It kind of produces very messy features. Like I'm not really sure what this means, because I don't know what kind of words you need to put in a neuron to predict your next token very well. You know, but this is okay, because when we do supervision tasks in the end in fine-tuning, we don't really care that our representations are intelligible. We care that they transfer. However, this also raises a bit of a question, and it might not, I mean, to me at least, it's a bit of an uncomfortable one, because what would happen if you have a self-supervised system that produces more intelligible representations? And how would you understand this better, if that helps or not, through more self-supervised evaluation? And I will kind of go with this thought into the rest of the talk. One final thing that we took out of the pre-training was basically, because we have part of speech tags, you can basically measure for each part of speech tag your frequency distribution for those tags on your corpus. And now you want to know, does your network activate similarly? Like, you know, but when it, are your activation patterns, the distribution, is it learned by your neural network? And we can see here the corpus frequencies in black, and in gray in the first episode, the learned activation frequencies, basically. And you also see that in red, later on, it matches even more. But from the very first epoch, we match this part of speech distribution quite nicely. And there was a work by, I hope I pronounced the name correctly, Chapra et al., who showed something similar. Basically, that part of speech tags are learned first by a language encoder, such as an LSTM. Now to kind of answer your question, Yanai, we have here the 0-shot setting, and this means, okay, you have now your pre-trained neuron preferences, and now you just apply new text to it. And by apply, I mean you don't tune your encoder or anything. You just get new preference distributions. And now what you can do is, because for some neurons, those preference distributions, they are very similar, which means you could actually reuse your old knowledge. And to me, in this case, this is what we define as transfer. If they change a lot, it means the preference of that neuron didn't really transfer to the new data set. So what this is measuring is not your distribution overlap between the old distribution and the new distribution, but between the distribution that your model learned with the new distribution, because it doesn't really matter what your original distribution is if your model didn't learn it. We also have this supervised fine-tuning setting. This is the typical, like, you know, self-supervised pre-training, then fine-tuning. We fine-tuned on the IMDb binary classification task, and fine-tuning also in the sense that now also the encoder is not frozen anymore. And then we wanted to know, because this is also an explainability method where you can visualize neurons, what happens to the preference of neurons. And we saw that even after this supervised fine-tuning, we still have some neurons that are highly preferred or less preferred. And we see that here in the middle. We have the least preferred ones, and preferred again meaning that they have maximum activations for any features. If we prune the least preferred ones, we basically reduce overfitting because we only lose training performance. However, if we prune the top 20 preferred ones, so the ones that by way of this method are detected as important, we also lose test set performance. What's more interesting is in this encoder that you see here on the right in the architecture, you can see that some units here are gray, which means they're not preferred anymore. Or even in the pre-trained encoder here on the left, some of them, they were not maximally activated ever, basically, for any features. However, supervision now added 85 of those maximally activated neurons, meaning it uses now neurons that before were much less used to store additional supervision knowledge, which is kind of interesting that it adds this additional thing. And if you prune that, you lose on your end task, obviously, a lot of performance. So another thing that we realized is that our encoder had, I think, 1,500 neurons, and 740 of those became unpreferred, with no more maximum activations in them. We call them here avoided, because they do not matter as feature detectors to the supervision end task. And if we prune them, we increase test set generality because they're basically noise to this end task. So what you can take away from this is you can basically find out which parts of your network, which neurons are not needed anymore, which ones are really important, which ones were added because of your new training signal, this sort of thing. Ah, yeah.
Hey, Nils. So
hey, wait. Yes, thank you.
Yeah. Why does the 700 something neurons don't then respecialize during fine tuning?
I think because here we are just looking at a very sparse notion of what's happening in a neural network, right? We are just looking at like the top line, only the maximum activations.
Mm-hmm.
And what this is saying is basically during pre-training, we used almost all of them. All of them were at some point maximally activated. And here, after fine-tuning, many of them aren't maximally activated anymore, which also makes sense because you turn off every knowledge that you had during pre-training by supervision, because you don't need it for the task, and because all these features are on all the time, because in the end, it's just a long sum that you compute for your activation. You have to tune them down. And I think this is exactly what's happening here for supervision. It learns to suppress anything that is basically not needed as a feature and just weights it down.
Is this
Does
some
that make
kind
sense?
of, I guess, is this a characteristic you think about regularization of these neuron weights because they don't matter what acts most on them is the regularizer, or is it just a characteristic of the fine-tuning in general?
I think supervised fine-tuning. So what you do is if you have, and you kind of see this in explainability, right? If you just mark in your input, what is your decision base for that according to some explainability method, this heat mapping, like where you have three red words, your decision base is very sparse. Out of a text of like 40 words, 5 of them are important, the rest isn't. And of course, if you have a target like that, a very sparse target like that, just 2 classes, you basically need to learn to turn off all these features that don't matter. And this is my interpretation of what is happening here. And because you have more than just these maximum activations, if you actually remove these now indicated as unpreferred, not maximally activated neurons anymore, you actually gain performance because you remove what is noise to the end task. But to me, it doesn't mean the network becomes more clever or stronger. You're just supporting in this kind of extreme bias you have in binary classification.
I see. Thanks.
So to me,
maybe I have a kind of follow-up question. So we know that there are many problems of like spurious correlations, especially like in the supervised setting. So like how do you think it's related? So like what you're saying that you see actually that features or like these neurons that maybe are related to some of these words, so then the network automatically kind of shut them down, right?
Yeah.
But how does it go with the spurious correlation phenomenon that we see?
I think I will get a bit more into that, but to give a small primer, I think if you have really large networks, let's say BERT and up, then you encode a lot of long tail or very like rare information, and you might call this seldom features or how you just called it, but they are always useful for some task, right? And I also think this is why when you pre-train on so much data and so many combinations, you can solve so many tasks better because each end task that you have needs other features. And the more of that you cover of this distribution, especially all the minute details, the better is your supervised performance in the end. And this is my understanding. And we choose here binary classification because, for example, in continual learning, we have this thing, if you if you have a supervised task and then you do another task after that, the new task completely overrides all the neurons that you fine-tuned for the old task. So you force this forgetting. And the way I see this is like, this is just what supervision does. It sparsifies your network because it's supposed to learn a very sparse output. Right? So I see this more from like an encoding perspective. Okay. Just to summarize this paper quickly. So our intent here was really that you can basically explore generalization and specialization of individual neurons. And what I just explained a bit is here, down here, you can see the red graph. Here, all the neurons from 0 to 1,300 sort of activation. And you get a very broad activation during pre-training. Then in the 0-shot setting, you still get a very broad activation, but you don't use all the neurons. That's why there's a bit of a gap here. And this is a, let's say, shorter distribution. However, after you do this reconfiguration, sparsification because of supervision, where you turn off a lot of weights, you get this really much shorter distribution here. Many less neurons are used. So basically, you can say it was sparsified in that sense. And because this here is in log scale, the activation mass that you have for the most active neuron, it gets really peaked. You don't really see that here because it's in log scale, that it basically becomes much bigger. So you get this really specialized distribution rather than this wide, broad distribution of activations. There's also some work I want to talk about reading that I would recommend or find quite interesting. There's one where they explain individual neurons in vision, where you can basically see objects, materials, things like that, which is really interesting to understand what's happening in your vision pipeline. There's an older work, Activation Atlas, and this one inspired the whole idea of that neurons should be explorable. However, the visualizations they did, they're kind of intricately tied to a supervised learning setting. And what we wanted to do here is say, okay, the method you use isn't really tied to supervision, so let's just use it for NLP and for unsupervised representation, and maybe start trying to remove this probing task limitation so that you can do this exploration sort of thing with the XAI component. And then because you're not deciding with your probing task what you want to find, you kind of delay your expectation bias. This is how I would call it. So you're not deciding early on before you do your experiment what you want to find. You kind of try to find that out by analysis. This is maybe not as clear as I personally think it is. Pruning, there's also a method that's called movement pruning. There's 1 or 2 papers on this, and they prune neurons that change during training and transfer. So this is quite similar to what we did here a couple of slides ago when we pruned the neurons that basically change their activation patterns, right? The avoided ones, if you prune them, you might get similar results as in this movement pruning paper. Okay, and there's also some open questions here and some caveats. First of all, and this is just my opinion, I think pruning is not a good idea unless you really just care about this one end task, and of course to shrink your model. Otherwise, I personally see it as forced forgetting, and I would expect your representation to become weaker because of it. So your test set generalization might go up, your usefulness of the representations for any other task, I would expect it to go down. And there's a bit of preliminary work by Vagish here on the right in his master thesis. He found out that when you predict many classes in a small model, pruning always hurts. And we kind of know this from the lottery ticket hypothesis, which is mostly about pruning, is that pruning only really works in overparameterized models. And so it's kind of useless when you already have a very small model you can compress. It's basically as easy as that. It seems obvious, but it's also easy to run into that idea that you need to prune even a small model, and it might not work. Then also another caveat of XAI in general, we know that in explainability, like this feature heat mapping, we know that it's very sensitive to supervised learning quality. So your explanations aren't good if your predictions aren't good, basically. And the same is true with interpretability, only that your self-supervised learning quality needs to be good. And we also saw this in early episodes. And that the network changes and stabilizes in later episodes. Of course, interpreting anything in the early episodes or pruning there wouldn't make much sense. You need to have an idea that your learning is done, basically. However, this is also sort of an advantage because even though it's very intricate, it might tell you that if your representations start looking better, you might actually do better self-supervised learning, even though you might not immediately be able to prove it with any probing task, because you might just not know what is the correct probing task to show the difference. We also,
Nils,
yes?
before you move forward, I think we have a question from Stagnik. If you're
Oh,
here,
oh yes,
would you
yes.
like to...
Thank you.
Stagnik, would you like to ask your clarification question? Oh, the mic isn't working, so I'll ask it. So before we move forward, I think I'm a bit confused by what we call neuron here. Can you please explain a bit? Are they different dimensions for, let's say, 764 bits of a word?
Mm-hmm. I think this refers to this slide, right? What I mean by neuron here, imagine this is your, for example, you have an encoder and you have in one of the layers, you have a bunch of neurons, your parameters, usually like your W matrix vector. So what I mean by neuron here is basically weights in a neural network. Okay.
I have a follow-up question.
Yes.
So about that, about, let's say, interpretability or kind of explainability, do you have any measures of the pruned neurons to linguistic features, such as specific words or maybe?
No, we didn't go that deep yet. That I mean, I understand the question. That makes absolute sense. Mm-hmm. However, we didn't do that yet because coincidentally, like I worked a lot on this with Vagish, like he's here, Vagish Saxena, and we are both really into how learning works, but not really dependent on the data. So we are more interested in the learning dynamics part. So that would be I think that's quite an interesting question, but we haven't yet.
So it's practically just, I mean, in general neural. So you apply for the general neural case. Okay,
exactly.
Wonderful. Yeah, it's interesting. Thanks.
Yeah, we didn't have a specific end task in mind with this. And this is kind of like this whole talk doesn't really have a specific end task in mind. Other than learning, better understanding learning dynamics in neural networks. So what we did is we also tried this method for evaluation, because I also wanted to talk about evaluation. And here we evaluate the preferred data sources and model components for a task. And this was in a recent paper. The task was, will the patient die in 24 hours? And in yellow here, you see that we have 3 data sources. And the first thing and here you see these activations summed, like the activation sums, basically. And the first thing that you can see is that these output events with liquids coming out of a person's body, they're apparently not very predictive of if a patient dies in 24 hours. Then at the lower layers, this was a simple multi-layer pooling model over time, meaning that a patient history to do this prediction, at the lowest level, you have these 1-hour buckets that have some features in them, like basically how's the patient doing in that 1 hour. And we found out that just looking at these graphs here in red and green, you can, for example, see this, that the average in some pooling operations at the 1 hour bucket level are really important, especially from chart events. So you can kind of tell which data do you need and which model components do you need, which ones are important in your model. And when we pool these 1 hour buckets over time, so 24 buckets basically, we get this average, max, and sum pooling. And again, we see that here, for example, this max pooling is very important. So we kind of know here for lab events, okay, pooling over time, we might actually not do it because it's not that important. So we could throw that out of the architecture. Digging a bit deeper into evaluation, and I really just want to use this as kind of like a hook to motivate these questions. What we do a lot in supervised evaluation is this kind of catch them all supervised benchmarking. And here's an example from my own experiments with that. So I took a word embedding benchmark, which has 18 tasks in them, or 3 categories. These categories are category, which is classification, analogy, and similarity. And we just took pre-trained and word embeddings that we either pre-trained ourselves or downloaded somewhere and put them through an autoencoder, basically to do denoising, if you will. And what happened is, if you have a dev set, you can always produce better retrofit or cleaned up embeddings, basically. Interestingly, what you could also do is you could produce embeddings very reliably, basically every random run would be better over all the 18 tasks. So you would end up with embeddings that are on average always a bit better. And this in itself isn't crazy interesting. What was interesting to me about it is that this is especially true, this performance increase from just retrofitting with an autoencoder. It works the better, the less data you have for pre-training. So it's really kind of aimed at low resource learning. However, the problem I discovered with this is you have a given set, your benchmark evaluates your evaluation models, your probe models. They have a certain depth or a certain complexity. Usually they're kind of shallow models. So what you're really measuring here is just how well your technique fits your probes. You're not really finding out which ones are the better embeddings. And I personally find this really difficult. This was also mentioned in a paper. There it was about, I think, more common benchmarks such as glue and NLI benchmarks, if I remember correctly. But the notion basically holds is your probes need to be strong enough to understand your representations that you're learning. Otherwise, it's kind of a question what you're really understanding then. And this is the second thing that I call your nagging question. What do these benchmarks really tell us? And how do we have to design them to be really that deeply meaningful? And also in regards to evaluation, we have a lot of SOTA score things still. And it makes sense because these papers are easy to get accepted. But we have recently also seen a lot of people pointing out that it's also a hardware budget question, that there's a lot of seat hacking, which means random seats, and you can get better. The more hardware you have, the better your seats are that you find in the end. And also people have noticed that in BERT, Electra, Roberta, and things like that, there's a survey linked down here. We have kind of increased the data size of pre-training in between a lot of these model iterations. So we don't really know if the models became better or the data just became bigger. So it's not really a controlled experiment in that sense. You should keep your data size the same and then compare the models, even though in practice that's not always possible, obviously. And one thing I want to point out here, from like the 1990s to 2010, machine learning was a bit this, like, if you have a lot of supervised learning data, you can get away with a simple model, and often it can also just be small because you have a lot of data. Since I would say 2016, 18, we are more on this, like, okay, we do this self-supervised now. So if you have a lot of self-supervised data, you can also get away with more general. Some people say that self-intelligence is a simple mechanism. I would agree, but it's a very complex one. Meaning many simple things make a complex thing still, and that models are now big as well. But it's still the same notion. If you have a lot of data, learning becomes easier. This kind of leads to the second paper I want to talk about, and this is how would you learn then from small data? And this is kind of trying to address these evaluation issues I just mentioned. And specifically what we wanted to do here is evaluate small data pre-training for few and zero-shot learning without large external pre-training data, which is the go-to method, and that you can also then run by yourself the pre-training on a few GPUs. And another thing that I personally think is very important, and I wanted to look at, is long-tailed and imbalanced data, because in your tail that you have in your distribution, you're always in a few shot or even sometimes zero shot regime, that you don't have labels for things. Let's say you have a data set and you have exactly one label for a class. As soon as you do train def test split, you are in a zero shot setting because it can only be in one of those splits. And the second thing is this tail problem of a data set. You can ignore it and make your data set nice, so learning is easier, or you deal with it, but then it grows with your data size. So this problem becomes worse the more data you have. And that's why I think studying it is interesting. So the problem then becomes how to learn a text encoder at smaller scale. And because of what I just said, basically what we want is zero-shot learning and long-tail capabilities. And there is work in this direction, specifically label embedding CNNs, where your label is assumed to be a word, because most labels you can express as a word. And if you can express them as a word, you can also assign an embedding to it, a word embedding. If you're interested in how this would work with a large pre-trained model along the lines of current practices, there is a label embedding BERT called XBERT. However, they realized that for the labels, the word embeddings you need for the labels, they needed to take them from Elmo, because it turns out that the contextualized embedding from BERTs didn't work as labels. And I think this is just a suspicion. Contextualized embeddings don't work well as labels because you need this global semantic of what the label means. So you need basically word embedding level semantics, not contextualized semantics. This is just my understanding of it. I'm not sure if this is true.
So could they just take the word embedding from BERT?
They tried that. It didn't work. They're basically, they couldn't use them well as label embeddings. Apparently for this task, they aren't good label embeddings, so they had to resort to Elmo. I think they also reiterated like 4 times on this paper. I'm not really sure why, but the whole thing, also with the second thing, at least as far as I could find it in the literature, I also found that basically CNNs and LSTMs, they were able to outperform transformer models when you only have small pre-training data. And those two things together, because of the zero-shot capability and the long-tail capability, we basically decided to go with CNNs in the end, to not have to deal with what is the best label embedding for BERT. And because they had iterated over this paper, I think by now 4 times, it seems to be a really difficult thing to do. So we ended up with this. And so basically, here's the model, and I will briefly summarize it. And what it is in the end is a self-supervised CNN-based pre-training. And you can see this as just one of many alternatives to transformer self-supervised pre-training. But this is specifically aimed at long-tail, low data regime, low pre-training data regime. So what happens here from left to right is you have up here in the left and up, you have your text. Down here you have labels, and these labels are now words. And you feed both your text and your labels into a shared word embedding layer, because labels are words. And what you get is you get your word embeddings and you get your label embeddings. and you feed your word embeddings into a text encoder and your label embeddings into a label encoder. In our case, the text encoder is a CNN. This is a simple, more like a fast text averaging with a small NLP on top. And then you get your text embeddings out here in gray and your label embeddings in either blue or red, depending if you have a positive or negative label. And positive label is what you get from your gold data set, from any gold annotations that you have, and your negative labels is basically some of your zero labels that you have, because they're still gold labels, but they're 0, not 1. And then you combine your text with each label. So you have to repeat the text for as many labels as you have, and you get this like text to label matching matrix that you can then put in a small matching MLP and train with a binary cross entropy, and you just say for every combination of label and text, match or not, 0, 1. So it's a one-class prediction problem, and you train it with binary cross entropy. If you have real labels, if you use real labels, you have the standard supervised learning setting, but with label embeddings. If you use words, you can just sample some words from your text that you currently have. These are positive examples, and you just pretend they're labels. And then you also have text from other instances, and words that are not in your current instances, they're basically negative pseudo labels. And using words as pseudo labels, you can train this also in a self-supervised manner. Because in the end, what this architecture does, it translates a sequence of words into a sequence of words and matches them. So it's still just a text-to-text prediction problem. How does this look in detail? Yes.
Boaz asks, what do you consider by small data?
Small data in the sense, in comparison to, if you look at current models, how they're pre-trained, I would say BERT, because it's big but not huge. We have in our experiments between 8 and 80 megabytes of text. So that might sound a lot, but I will go in a bit into the long tail problem, and you can really see that if you predict hundreds of classes over that, it's still way too little data. Most instances have like 10 labels or something like that. So you're really in a regime that is kind of hard in terms of prediction. Okay.
Another question we have from Dori is, what does the text have, or why does the text have multiple labels? Whether is it a multi-label scenario?
Okay. So basically, the data set we took here, I haven't really talked about that because it's more about the general idea. We took online questions for this, and they are tagged by, I think, maximum 4 tags. So you have like usually 600 words or something like that on average. And you're supposed to tag this online question on Stack Exchange, I think it is. So for example, is it p-value? Is it about the programming language R? Things like that. And if you think about that task, even for a human, if you were just given the question and no one tells you how many question tags or labels to put, it would be kind of hard to decide that you only, and find out that you only have to put 3. So this is kind of, we choose this because it's a typical, you get a text and you predict some other text, in this case, labels that are also text. Does that make sense? Somehow? Okay. Okay, so how do you train this? The objective here is not crazy new. It's noise contrastive estimation. The most prominent case where you might have heard this is word2vec. Noise contrastive estimation is binary cross entropy, where you have 1 positive and k negative examples in the typical case. However, as I just mentioned here, we have G positive and B negative, so good and some bad samples. And then you still have your standard BCE summing over all these separate instances. And this has also been done in previous work as linked here. The only thing that we really add is that you use input words as positive and negative labels, basically. So this extends the whole thing to be self-supervised. And if you wanted to give it a name, what you're basically doing is you're predicting some words of your input, which is autoencoding. It's also something that BERT does, even though it does it in a mass fashion. And it's contrastive because you have this negative sampling in it. So it's a contrastive partial autoencoding approach, if you care about it in machine learning terms. And what you end up with is this kind of using words as pseudo-labels for self-supervision is that you get innate zero-shot capabilities with this kind of loss. So what NCE gives you is it allows you infinite label sets and vocabulary sets. Of course, in practice, they're never infinite. But what you're basically doing here is you're undersampling your softmax. Again, if you remember word2vec, which removes one thing that, I mean, softmax is typically regarded a compute bottleneck in many architectures. And you still stay in this text-to-text prediction problem, but now instead of text-to-text, you predict embedding to embedding. So you have no more translation from dense embedding representations to sparse labels. You just stay in the same space, so you don't have to learn this translation. It also means that now your labels have semantics in the same way, at least weak sense, that word embeddings have semantics. And this makes sense because if you ask a human, for example, can you tell me what class this picture of an elephant is? They won't tell you, yeah, it's a 1 in the 5th element of that vector. They will tell you it's an elephant. So it has a meaning. Like it isn't this anonymous 0-1 thing. And one neat thing that comes out of this is usually you pre-train your inputs. Once you pre-train your inputs and you use your input embeddings as labels, you also pre-trained your labels, which means you also have immediate transfer between inputs and labels because they have a similarity. A last thing that you can do, though we didn't in the paper, if you had unknown labels that occur later on or unknown words, there's techniques to infer, especially also for rare tokens and words, or in this case labels, you can use something like attentive mimicking to get representations for those. So you can potentially add classes while you go. This is also why I refer to this as a zero-shot setting. This should be in there, in my opinion, this capability. Now, for the last part of this, yes?
Oh, sorry. So when you say that you get some supervision also for the labels, so in the zero-shot setting, it doesn't really hold, right? Because like in the zero-shot setting, you get new labels, so you don't really get supervision from the training.
It depends, because if you only sample some words that you get, and now you might get a new word that you haven't seen during training yet, you would need, in order to use that as a pseudo label for self-supervision, you would still need an embedding, and you can either just randomly initialize it and learn it as you go, which I think would be fine, or you could have these like more clever techniques, basically. Well, fastix isn't clever, but attentive mimicking is sort of. There you could really start off your label well initialized, so that basically if you find a good embedding for this, you should have good zero-shot capabilities from seeing your new label or using your new label the first time around. That's kind of the idea. Okay, so we evaluated this in a supervised setting, but I won't go into that because it's not crazy interesting, to be honest. But also in a zero-shot, few-shot, and a long-tail learning setting to dig a bit deeper into what's happening. What you can see here is the lowest graph, this light blue. This was our supervised standard configuration, basically your best configuration for supervised learning, optimum found by hyperparameter search. And what we wanted to try out for zero-shot learning is first in the middle graph, to touch none of the hyperparameters, but just to do more sampling. So just to add more random words for self-supervision. And what happens is just increasing the self-supervision signal already boosts your zero-shot performance. So zero-shot performance meaning supervised performance on the end task without ever having used labels. Then if you also, and this is the upper graph, not just use more training signal, but also a bigger model to store all those variations, you get, again, even a higher boost. So my takeaway from this was you kind of need, in order to store this additional information, of course, you need some more parameters. And I will go a bit into how this relates to the long tail problem in a moment, and also what I think is the connection to large scale pre-training, because you already asked this question very early on, Yanai, if I remember. A second thing we wanted to do is few shot, zero shot, meaning few shot usually means you use less labels. Let's now assume that your only labels that you have are no labels. It's unsupervised. You only have pseudo labels. So what you do here is you use even less data of your pre-training data. So you use less text, few shotting the zero shot learning signal. And what happens is at 100%, you get this best curve. It's also the fastest and peaks out the earliest. But you can also see that if you go down in the percentages to even 10%, you still have these curves climbing. And many of them look like they're eventually going to climb to the same performance, even though we stopped too early here to really see this. My takeaway from this is simply, you can get away with pre-training on a lot less data, but you just need to wait longer. And what that means is, because this uses the same amount of sampling of pseudo labels per episode, if you use half the data, you only get the same amount of training signal after twice the epochs, right? So this is also why it now takes longer, because you're not just using less data, you're also providing less learning signal, because you give half the learning signal if you cut your data in half. This is not super surprising, like any of these insights. However, I did find it a bit surprising, because what is sort of an insight here is, when you don't have large external data signals for pre-training, you can also just increase self-supervision and might get better performance. And this is true despite this long tail problem worsening in the few shot setting and in the few shot setting. This means if you had 10 labels before only using 1/10 of the data, now you only have one label for a particular instance. So your learning becomes much harder, but this still works, the self-supervised pre-training with pseudo labels. Few shot setting. Basically what we see here, this is also trained with label embeddings, but only supervised label embeddings. So only with real labels and some negative real labels. It's not with pseudo labels. And what you can see here is, yeah, it kind of works, it's fine. But you also get these sort of learning plateaus here with this orange circle, that if you use early stopping too aggressively, you might get stuck in that, especially when you use a lot less data. So here, 10 or 25% of your data. When you do your pre-training first, and then you fine-tune this, so you do your self-supervised label pre-training, you don't have these problems. You get much more stable learning curves. Your end performance is higher, as you can see here. And very interestingly, even on the first epoch, you start off quite a bit further from zero than in the non-self-supervised pre-training scenario, where you basically always start out with your performance at zero. So basically, your learning just becomes more efficient and faster overall. And a last setting I want to talk about. So this is actually how the class distribution of this thing looks. And note here that the class frequency is here on the y-axis, and these are the classes sorted by their frequency, 1,300 classes altogether. And this is in log scale. And now we wanted to basically create 5 chunks, 5 class buckets, and they should all be balanced, which means the frequency of labels, active labels, positive labels you have in each bucket should be the same. And that means that in the head bucket, you have only a few classes because they're very frequent. In your tail, bucket, it has exactly the same amount of positive labels, but much more classes because they're rare. So 5 buckets that are balanced, the classes within a bucket are not balanced. And what happens now if we look at these 5 buckets that I just showed in color is on the left you have the head, on the right you have the very tail. You can kind of see how much long tail performance you really get. And here in black you see this like 0-1 prediction binary cross-entry baseline. Then in the middle you see the supervised and self-supervised label embedding approach, and then the model I talked about in the 0-shot setting where you make pre-training even larger and add more supervision signal. On the head, basically here on the first 2 bucket, it compares in terms of performance, but where you really gain performance is then in the tail. So in basically the red and the orange areas. And the last thing we wanted to kind of know is, okay, what else happens with the learning because of the stability, it learns faster, whatever. What does this mean for the long tail? And here you can see the baseline, and then in the middle in lilac, purple. So the self-supervised label embedding pre-training, and again the larger pre-training model in turquoise, I think it's called. The lower 3 curves are in the first epochs, 1st or 10th epoch, depending on the model. For example, the black baseline model here, it needs 10 epochs to have any measurable long tail performance in the last long tail bucket. Right? And you can see that here in the first epoch, self-supervised pre-training fine-tuned model with label embeddings already starts off better, and then in the optimal epoch has a better long tail performance than the baseline. And again, what we see, especially in early epochs, that the larger pre-training model with more self-supervised learning signal learns the long tail early on. And also, if we look at the epochs here, optimal epochs, it's compared 94 to 35. It learns almost 3 times as fast. So you actually, even in this very small data regime running self-supervision, my insight here would be you need larger models to encode the long tail, to encode all these nuances, not surprising, but also your learning gets a lot faster because this is exactly what the problem is here, to learn the long tail. This is what dominates this data set. And my reasoning would be, at least in this sense, even though we showed that you can do pre-training for small scale data, if you do it on large scale data, you might have very similar problems, and you might also get the same performance boosts out of using a larger model. This would be my reasoning. However, this is just an opinion at this point. Yeah, and this is just a summary basically of what we talked about. So how to use self-supervised XAI, that it can be used for transfer analysis, then that it might be interesting to learn to do this low resource evaluation, especially also with the long tail, and that the long tail remains a problem independent of your data size. However, this is also very nice because it means that you can also train on small data sets that have these kind of more, let's say, challenging problems in them. And that means more people might be able to do it. Like you don't have to use TPUs for this, basically. And then in the learning part, and just to summarize this, basically, if you do self-supervised pre-training on small data, you can get away with just using a bit more pre-training signal rather than having to collect more data. And with that, I conclude my talk.